I see a question up on the board here right now, guys. I want you to solve this question, solving for the acceleration of this 5 kilogram object, assuming that is that this object isn't being lifted up into the air. Okay, so we'll assume that it isn't being lifted up into the air. It's going to go horizontal. What is that horizontal acceleration? All right, it's time to take a look at this. First thing we got to do is draw a free body diagram. Okay, part of it's already drawn. We have the applied force of 20 newtons acting up at an angle of 30 degrees. We also have a force of gravity acting down on this. Okay, gravity acts down on it. And we also have a normal force acting up on this 5 kilogram object. Is this force, the normal force this time, going to be the same value as gravity? Is it going to be more than gravity, or is it going to be less than gravity? It's going to be less than gravity. Can you explain why it's less than gravity? Yes, yeah. Essentially, the y component of this applied force, there's an x component, we'll call it fx, and a y component, we'll call it fy. The y component helps the normal force. This thing needs to be pushed up with the same force as gravity is to balance it. But it's not just the normal force that's doing it. It's the y component of the applied force as well. So if we take that normal force and we add it to the y component of the applied force, then we will get the force of gravity. Now, we didn't actually have to do that in this particular question, but that's why the normal force is drawn shorter or a smaller value than the force of gravity. That's going to become important in the next question that I ask you. Okay, so make sure that you understand that. If you don't, then ask a question. All right. The normal force and the force of gravity and the y component of that force, the three of them combined do cancel out. That means I'm left with only one force, and that's the x component of the applied force. Let's find out what that is. Let's get it. Okay, I know that cosine 30 degrees is equal to fx. That's the x component over the hypotenuse, and the hypotenuse is 20 newtons. That means that fx, the horizontal component of that 20 newtons, is going to be, what, 17.32, I think it is? 17.32 newtons. So now I can do my whole net force thing. My whole net force is equal to the sum of the forces, which is easy in this case because I only have one force. The other one's canceled out. F net is simply equal to Fx in this case. M times A is equal to Fx, or we'll say the mass of 5 kilograms times the acceleration is equal to 17.32. 17.32 divided by 5 is going to give me somewhere in the range of 3.4-ish. Somebody have an is it 3.4? 3.46, so we're going to make it 3.5 then. How many people got an answer of 3.5 meters per second squared? Okay, good. For those of you who didn't get that answer, does it make sense? Let's change this question. We'll keep the basic structure of this question so that we don't have to do all of our calculations over again. But this time we're going to add friction to it. Okay, this time we're going to add a force of friction of 10 newtons. Which way is friction going to act? This block is going to move forward, right? Which way does friction act? It's got to act backwards. So let's add the force of friction in there of 10 newtons. Let's get the acceleration now. I think it's going to be a greater acceleration or a smaller acceleration? It should be smaller, right? Because now you got two forces opposing each other. They're not going to balance, but they are going to oppose each other. Okay, let's get the acceleration now. Notice I haven't erased this. I haven't erased this stuff because this analysis still applies. That hasn't changed just because we've added friction in there. All we're doing is changing the whole net force thing when we add friction in there. All right, let's take a look at this one now. We're going to do almost the same thing. We're going to say the net force is equal to the sum of the forces. But there are two forces now that haven't canceled out. Force of friction and the x component of the applied force. So let's say Ff plus Fx. And the net force is m times A. It's equal to FF plus FX. Plug in our numbers here. M is 5 kilograms. Got A. FF is negative 10. 10 to the left, so we make it negative. And then we get 17.32 over here for FX. 7.32 divided by 5 is going to give me somewhere in the range of 1.4 meters per second squared. How many people got that one? Okay, good. Let's change it one more time. Instead of adding a force of friction to the left of 10 newtons, let's add in a coefficient of friction. This is going to make it the hardest one yet. Let's add in a coefficient of friction of, let's make it 0.25. Let's make it 0.25. Now I want you to find the acceleration given the coefficient of friction, not the force of friction, but the coefficient of 0.25. To solve this question, we're going to need to find the force of friction. So let's try to do that right now. We've still got the x component of the applied force. We're going to still need that. Okay, we still recognize that gravity cancels out with normal force and the y component combined. Let's get that force of gravity, that normal force right now. Not the normal force, the force of friction right now. FF is equal to mu times the normal force. That's equal to 0.25 times, what's the normal force? As I was walking around, I saw a few people say the normal force was 5 times 9.81. 5 times 9.81 is 49.05. Is that right? Cassidy, why is that not right this time? Yeah. The normal force and gravity, you see, don't cancel with each other. Rather, gravity cancels with the normal force and y combined. Look, Fn plus Fy is equal to Fg. Okay, we need the normal force, but it's not 49.05. The good news is we can find it relatively easily. Okay, let's get the y component of that force here first. Let's say sine 30 degrees is equal to the y component over the hypotenuse. So Fy is going to be equal to 10 newtons. Now let's say the normal force plus 10 newtons equals 49.05. That makes Fn equal to 39.05. Do you see how the normal force is smaller than the force of gravity here? Because it's being helped by the y component. It's like the analogy that we gave you yesterday. Right? You're trying to lift something heavy in water. You lift something that has a mass of 20 kilograms on the land, it's heavy, right? It's 50 pounds, it's heavy. You lift something that has a mass of 20 kilograms in the water, it seems lighter because the buoyant force pushing up is helping you. Well, the normal force pushing up is being helped here by the y component of the applied force. So the normal force only has to push up with 39.05 newtons. So let's plug that value in here. The y component, 39.05 newtons. Now 20.25 times 39.05 is going to give me almost 10. What is it, 9.5, 9.3? 9 point what? 9.7625, thank you. 9.7625 newtons. Now the question is really just the same as the last one, right? Now that we've got the force of friction. So let's say the net force is equal to the sum of the forces. That's FF plus the x component of the applied force. The mass is 5 kilograms times the acceleration is equal to the force of friction, which is negative 9.7625 to the left, plus the applied force x component, 17.32. What do we get when we do the math on that one? 17 minus 9 divided by 5. 1.5-ish, I think it was. 1.5? Okay, here's the real question. How many people got that one? Okay, that's not bad, actually. It's not bad. Okay, there's still quite a few of us that didn't get it, but it's not bad. Does that make sense to us? The real trouble with that was the normal force, I'm sure, wasn't it? Is that it? Those of you who had trouble with the question, the normal force? Okay. Up until recently, we said the normal force was always equal to m times g. But if you remember those questions, the object was always being pulled horizontally. It wasn't being pulled upwards. Now it's being pulled upwards. The normal force is being helped. So we've got to remember that. We've got to remember that normal force isn't m times g anymore. It could be sometimes, but it's not if it's being helped. All right? All right, we also had one more question that we put on the board yesterday that I asked you to solve for homework last night. Let's take a look at that one. The problem was find the force, find the net force due to these other three forces that are acting on this object. So it's your bag of Halloween, bag of Halloween treats, your bag of toothbrushes and gum, if you go to the wrong neighborhood, right? Your bags of toothbrushes. What's the net force acting on this Halloween bag that's being pulled on by three different people in three different directions? Well, the first thing we do here is see that 60-degree angle and kind of say to ourselves, we don't like funny angles. So let's get rid of that funny angle. Okay, let's turn that funny angle into something that's to the left and something that's up. Let's do that off to the side here. I got 60 degrees right here. I've got 15 newtons right there. I've got an x component. I've got a y component. We're going to say that cosine 60 degrees is equal to x over 15. And x equals 15 times cosine 60, which is 7.5 newtons. We're going to say the y component is sine 60 is equal to opposite of hypotenuse. Y is equal to 15 sine 60, which gives me 12.99. So far, so good? We want to get rid of that funny angle, so we turn it into an x and a y. If we really wanted to, we could replace that with a 7.5 Newton force this way and a 12.99 force this way. That would be the same thing, wouldn't it? And now we don't have any funny angles. Okay, we don't have to redraw the picture like I have right now. In fact, I don't usually do that myself. We had a force of 15 newtons that we called F3, and it acted at 60 degrees. But it's the same thing as saying we have one to the left that's 7.5 and one that's upward of 12.99. All right, let's do our components here. We know we got to do components. The x says the net force is equal to the sum of the forces. That's F1 plus F2 plus F3. What's F1? Remember, we're doing x components here. What's F1? Alex, what's F1? Good. 0 because it's straight down. What's F2? Yep. It's 12 newtons, and it's positive because it's to the right. What's F3? How much of that 15 newtons is left or right? Good. Negative 7.5. Why the negative, Josh? It's going to the left. 12 plus negative 7.5 is going to give me 4.5 newtons. Okay, there's the x component. For the y component, we're going to say the same thing. F net is equal to the sum of the forces. We have done this hundreds of times now. F net is equal to the sum of the forces in one context or another. You see how they're all kind of the same as each other. What's F1 for the y component? Nick, what's F1 there for the y component? Nick? Good. It's negative 10. Negative because it's acting downwards. F2 is what? What do we have for F2? It's 0, yeah. Why is it 0? Because it's going to the right. Good. And F3 is what? 12.99, positive? Because it's upwards. We add those up, we get 2.99. Now what do we do with these two forces? The x component, 4.5, and the y component, 2.99. Yep. Yeah, a vector diagram, right? Let's do a right-angled triangle, a vector diagram. Okay? We've done this a million times before. Not always in this context. We've done it a lot with displacement vectors. We did it a lot with velocity vectors in the last unit. This is no different. You got an x, you get a y, you put them together. We got 4.5 to the right. We get 2.99. It's upwards. We want to find that force, and we want to find that angle. Let's say F is equal to the square root of 4.5 squared plus 2.99 squared. And then theta is equal to the inverse tan function of opposite over adjacent. Is that good? What's that answer we're going to be, by the way, for F? Somewhere around 6, 5 or 6, 5.4. And what's the angle we're good to be? I'm going to say 30. What is it? 34. How many people got that? Okay. Let's take a look at this one. This is the only other real sample problem that I want to do with you here today. This looks kind of different. It says a store sign that experiences a downward gravitational force of 245 is suspended as shown in 3.18. That word suspended is kind of key. We see that a lot in Physics 30. There's a number of questions where a charged particle is suspended in a magnetic field, or a wire is suspended in an electric or a magnetic field. Or you don't know how to do that question yet. Right? But you do know that if something's suspended or hovering or maintaining its same position, you know the net force is equal to 0. Okay? Something's not going to sit in one place if it has an unbalanced force acting on it. So if it's suspended, all of the forces must balance. That's the first thing you got to take away from this. All of the forces have to balance in both the x and the y dimension. All right. If we know that, we've got a fighting chance at solving for Ft1, which is the force of the first rope, and then Ft2, which is the force of the second rope. Let's draw a free body diagram. It's largely drawn for us already. We have Ft1 drawn for us to the right, drawn up and to the left. We have Ft2 drawn for us to the right. The only force we're missing here is what? On our diagram, at least, the only force we're missing is what? Maddie, what's the force that we should put in here that's not there already? Yes, the force of gravity. It's going to be 245 newtons. We'll call that Fg. Now, we don't know how long to draw that relative to my other forces because we don't know what the other forces are. That's okay. Okay, I'm not going to mark you wrong because you haven't drawn the wrong length relative to the other forces. What should we do to start, do you think, now that we've got our free body diagram drawn? Any ideas? Well, are all these forces acting on the same plane? Are they acting in the same dimension, x or y? I can see that one force, Ft2, is acting in the x direction, Fg is acting in the y dimension, and Ft1 is acting in both. So they're not on the same plane. If they're not on the same plane, what do we always got to do? Here's x, here's y. Now, for the x dimension, we're going to say Ft FT1X, sorry, we're not going to say that yet. We're going to say the net force is equal to the sum of the forces. Now, the sum of the forces includes all three of these, but the x component of all three of them. So we'll say FT1 x component plus FT2 x component plus FG x component. I told you the answer to the next question already a few minutes ago. What's the value of F net? If it's suspended, F net must be 0. The forces have to balance. So let's plug that in as 0. We could say m times a. That's fine. But a is 0. If it's not moving, the acceleration is 0. We don't know what FT1x is. We have no idea because we don't know what FT1 is. We don't know what FT2x is. We have no idea. We do know that Fg, the x component, is 0 because it's all acting down. That doesn't seem to be much help. I've now got an equation that says 0 is equal to F1 plus F2 plus 0. There's two unknowns in that equation. I can't solve for either one of them. So what next? Mason? Do the y. See what comes out of it. Look, if we end up in a situation with the y component like we did with the x, with two unknowns, that's a problem. Okay, but right now we're not stuck because we have one more thing that we can try, the y component. So let's do it. Let's say the net force is equal to the sum of the forces again. That's going to be FT1 y component plus FT2 y component plus plus Fg y component. What's the net force again for the y component? We know this, right? Olivia, what's the net force for the y component? No, the net force is still, right. The net force is still 0 because it's not moving. So the forces have to balance out. FT1 y component, we don't know. Not starting off good here. FT2 y component, Josh, this is good news, right? We know this one is 0 because it's all horizontal. Fg y component is almost 245. Good, thank you. Negative 245, Devin, thank you. Well, now we can solve for FT1 y component. It's going to be equal to positive 245 newtons. Okay, that's good news. We have something. I don't have a final answer yet for anything, but I've got something. Can I take that value for FT1 and plug it in over here? Who says yes? Who says no? Okay, lots of people aren't sure, but lots of people said, no, we can't. Why can't we? Lane, why can't we do that? Yeah, it's a funny angle, but why can't we take that value that we just found for FT1 and plug it into the other FT1? Okay? Good. We just found the y. That's the x. But we can get the x from the y. Okay, let's draw that up here. Lane, you're not completely off base there. Okay, we've got that funny angle. We don't like funny angles. We can't get rid of it right off the top because we didn't know what its value was there. Okay, but now what we can do is say, look, FT1. Okay, FT1 is right here. This is 55 degrees. We know what the y component is. It's 245 newtons. Let's get the x. Okay, let's get the x component. Let's say tan 55 is equal to x over 245. That's opposite over adjacent. 245 times tan 55. We get 349.896. Is that right? Somebody else calculate that? Yes? Just didn't seem right there. 349.8963. All right. Now we're going somewhere here. The x component of ft1 is negative 349.8963. Negative because you can see in that picture it's going to the left. The x component of ft2, we don't know, but we can now find it. ft2x has got to be equal to positive 349.8963. Yep. Wouldn't the x, oh, yes it is. I think I got that backwards. That's why the number that I got didn't make sense to me at first. Yeah, you're right. Thank you. It's going to be, I went adjacent over opposite, didn't I? So it's going to be, let's change that number. It's going to be opposite over adjacent. It's going to be 245 over x. What does x work out to be there? 245 over 1055. 171. That's better. Doesn't change the basic way that we do the question, but it does change the number, obviously. So this is going to be negative 171.551. That makes ft2x positive 171. Okay, what were we asked to find in this question again? ft1 and ft2. Do we have the value of any of those yet? Are we done? Just about. We've got this one, right? ft2, it's only x component. So we just found the x component of it. We're done that. It's going to be 172 newtons. Do we have ft1? No, but we have ft1x and ft1y. We could find ft1, right? How are we going to find this value right here? Which is really what we're looking for. How are we going to do it? Yeah, you got a couple of options here. In fact, you get 3 options, 4 options actually. 3 of them involve trig. 1 of them involves the Pythagorean theorem. So you said a squared plus b squared equals c squared. That's absolutely fine. What's your method there, Hayden? 245 divided by cos. Yeah, let's use the cosine function or the sine function, right? I said 4 options, it would be 3 options. I'm going to use trig, but if you want to use the Pythagorean theorem, that's fine. Okay, let's say cosine 55 degrees is equal to x, which is 171.551, divided by the hypotenuse. What does that work out to be? 171 divided by cos 55. Sorry? 299? So now I'm done. And there's stuff all over the place here, different colors, whatever, but like let's not lose sight of the main part of this question, right? What did we do? Same thing as we always do. We do a free body diagram. And then what did we do? Well, we said F net is equal to the sum of the forces, but we did it in 2 dimensions, x and y. Then we realized we were missing some stuff. Okay, we had too many unknowns. So we analyzed that triangle, okay, and then we went from there. Okay, these are doable questions. That's a hard question, actually. It's a tricky question, but it's a doable question if you just take it step by step, bits and pieces as you go. You don't get flustered by it when it looks hard right off the top. All right, I'm going to give you a chance to finish copying that, and I do want you to make sure that you have that copy down because this is your recipe for the next few questions that you're going to do. You have that recipe beside you. Okay, literally on a separate piece of paper right beside you as you're working on the next few questions over the next little while. Ask me questions, but check your recipe first. All right, guys, you got a chance to write that down. Now let's take a look at these questions, please. Let's do questions 1 and 2. Let's not worry about question number 3, okay? 1.35, questions 1 and 2. I'll copy over the sign-in example 3.4 as well onto this page so you can have it all in one place, okay? Once you finish those 2 questions, please keep working on them if you're not finished. But once you are finished, then I want you to do 3 more questions. Check and reflect questions on page 136. I want you to do only 5, 6, and 7. Okay, those are your homework for tonight. The 2 questions that you're working on those practice problems, and then check and reflect questions on page 136, number 5, 6, and 7. Now, 7, okay, you can see the angles. It looks a little bit different than the problems that you're working on over the last few minutes. It's the same basic idea. Question 5 and 6, a little bit different here. These are like the problems that we were working on before, these sign problems. I'm going to draw each of these for you, just so that you get these angles straight. Person A applies a force at 45 degrees. That's going to be this way. So we're going to say FA is 80 newtons at 45 degrees. 345 degrees is this way. Okay, it's 15 degrees right there. And we're going to call that FB. And has a value of 90.0 newtons. You're looking for the net force on the tree in that problem. Now in question number 6, you've got 3 forces. One of them is acting at 30 degrees. We're calling that F1. One of them is acting at 115. We're going to call that F2. And 115 degrees is going to be 65 degrees right here. And the third object is at 235. That's going to be at 35 degrees right here. So copy those pictures down if you're having any trouble with that notation of those angles at all. You don't have to know this notation, by the way, the 235 and 345. Don't worry about that. Okay, that's why I've drawn these diagrams for you. If you know them, that's great. If you don't, then make sure you copy down those diagrams so you can do these questions. And I'll leave that up for just a moment here, and then I'll flip back to the other page so that those of you still working on those practice problems can finish those up.